Today is the second day of clear sketching, so that's what we're going to get ready to do. We're going to analyze this graph in all the different ways that we've learned. What makes this most difficult is dealing with the idea of the x to the fourth power and then solving for that. So we're going to jump right into this. And I'm going to skip over finding the intercepts at this point in time because it is an x to the fourth. I'm going to say that I have 4x cubed minus 24x squared plus 36x minus 16. That would be my first derivative. After that, we will say something equals 0 and factor out of 4. That will make things a little bit easier. That's still a cube function, and I can't really group it or anything like that. So if you guys go back to Algebra 1 and you think about one of the rules that you guys learned, you learned how to make factors out of larger polynomials, and you did that with the coefficient out in front and behind. And you'd write down all the pairs. You'd say, well, you're going to use the 4 over 1, and then you'd write down all the different options. You'd write down factors of 4, which would be plus or minus 1, plus or minus 2, plus or minus 4, and you'd use those to try it. So that's really what I'm going to have to do, is I'm going to use synthetic division, which means I'm going to put a 1 in here, and I'm going to try 1 first, only because I know it works, and we'll go from there. How do I know it works when I get a 0 here for my remainder? Synthetic division says you write down all the coefficients of your polynomial. You bring down the 1. 1 times 1 is 1. Add these together. Get negative 5. Negative 5 times 1 is negative 5. Add those together, you get 4. 4 times 1 is 4. And you end up with 0. So going back up to what I've written here, it would now factor into x minus 1 times, this is my new polynomial, this is the coefficient in front of the x squared, this is the coefficient in front of the x, and then I have plus 4. Good news is that I know how to factor the second quadratic. It's x minus 4, x minus 1, so 1 ends up being a double root. So my critical numbers are 1 and 4. And I'm going to test the intervals of those. So I'll put 0 in for my derivative. And when I do that, I get it with a negative number. When I put 2 in for there, it may be easier to look at the factored portion of it. So it would be 2 minus 1 is 1, 2 minus 4 is negative 2, and 2 minus 1 is 1. So I do end up with another negative here. And then lastly, I would try and 5. And when I do 5, I end up with a positive. So this is kind of odd. We don't normally see this happening, but we'll be able to look at that a little bit further once we look at the second derivative. So the second derivative is taking the derivative right here. I only really need to take the derivative of this part right here. So I've got 3x squared minus 12x plus 9. So when I factor out a 3, I have x squared minus 4x plus 3. And I end up getting x minus 4, x minus, let me make a correction there, x minus 3, x minus 1. So I have possible points of inflection at 1 and 3. When I test those for possible points of inflection, I will see that when I put 0 in here, I get a negative value times a negative value, which is positive. When I put 2 in here, I get negative times a positive, which is negative. When I put 4 in here, I end up with positive times positive, which is positive. So what does this graph end up looking like? Well, I actually need some ordered pairs, and I'm going to just tell you what these ordered pairs are. Remember, you get those by plugging them back in here for the y equals equation. It'd be 1, 0, which happens to be an intercept, and you'd have 4, negative 27. And this value of 3, I don't have an ordered pair for that, and that doesn't really matter. I will end up just needing to finish this on the next video. I was going to try to hurry through it, but it's not going to work. So taking a minute, these values, this y value right here is found by taking the 1 and plugging it back into the original problem. That would take me a while to go through on the video, so I'm not going to do that. And the negative 27 is also found that same way by plugging 4 in for here and getting those values. So 1, 0 is actually right here, so I'm going to start to plot that dot. I also can find my y-intercept because it's probably going to cross over here by plugging in 0. So when I plug in 0, I get 0 all the way across and I get 5. So I know I have a y-intercept of 0, 5. So I'll plot that dot. Now after that, I just have to look at how this is decreasing and decreasing some more. So there is no max or min right there, but this still is a critical number for some reason. And then we have an increase here, so I know that there's a minimum at 4, so this ends up being my minimum. And since I can't go down 27, I'll just go down a lot, and I'll just say this is negative 27 way down here. So what happens is I know it's decreasing, and to 1, it's also concave up. So it's decreasing and concave up. Then at 1, it changes concavity and goes concave down, but it's still decreasing. And then once it hits 4, it starts increasing and it changes concavity again, and then goes concave up at that point in time. So this is just a brief sketch of that picture. It's not exact by any means, but we've gotten the idea of it. Increasing and decreasing, you should list down that it's decreasing from negative infinity to 1 and from 1 to 4. It's increasing from 4 to infinity. You should also mark down that it's concave up from negative infinity to 1 and from 3 to infinity. It's concave down from 1 to 3. All those things should be written out. This next example, really, anytime we have an absolute value, what we're going to do with it is just graph it. We know it's a v. We have difficulties taking derivatives of absolute values. We actually don't do that a whole lot because it's just kind of a waste of time. We know what absolute values look like, so let's just sketch this graph. The only thing I will do is I will go ahead and find the x-intercept of this graph. The x-intercept is 3/2. So right there. The y-intercept, when I plug in 0 for the x, ends up being a positive 3. And if I wanted to just get some other points, I could plot them. But I know that because this gives me 0 here, it's where it changes from positive to negative, or where this gives me 0, it changes from positive to negative. So I know the graph just looks just like this. And I would just state that it has a minimum at 3/2, 0. And I would really be done with this because there is no points of inflection. There is no asymptotes. We've found the x and y intercepts. There's really nothing more to do to this one. I will start this last problem on this. Hopefully I'll get through maybe the first derivative. So when you're taking the first derivative, I would go ahead and distribute the first part. And then the first derivative would be 2 and the derivative of plus the derivative of cotangent is negative cotangent squared x. We want to know where is this derivative from. So we move cotangent squared to 2 and solve. Well, I don't know a lot about cotangent, but I know a lot more about sine squareds, or sine x squareds, because that's what cotangent 1 over sine x squared of 2. This one ended up giving me 1 equals, once I cross multiply, 2 sine x squared. So I'm really looking at where is the sine of x squared equal to 1/2? Or really, what is the sine of x equal to the square root of 1/2? Alright, finishing up this problem. This right here, the sine of x would be equal to 1 over the square root of 2, which is the same thing as square root of 2 over 2. And so where does this happen in this interval right here is at 45 degrees and 135 degrees. So I will take those two numbers and put them on a number line, which is 45 degrees corresponds to pi over 4, and 135 degrees corresponds to 3 pi over 4. We need to test the interval. The only interval I'm going to try here is right here, pi over 2, because this is a polynomial. I know that it's just change signs after that. I'm going to actually take that right up here and plug it in. So I actually want to think about this as being 1 over the sine of x squared. And I'm going to put in pi over 2, like I said. So I'm really thinking, what is the sine of pi over 2? Sine of pi over 2 is right up here. It is equal to 1. So 1 over 1, this is 1. 2 minus 1, oh, that's a positive answer. That means that these have to be negative on the other sides of them. Because it's a trig function, I know that is going to change, increasing and decreasing. The second derivative then ends up being the derivative from right here. So the derivative of 2 is 0. And then the derivative of cosecant squared. It may be easier for me to first rewrite this first derivative. So the first derivative would be 2 minus cosecant x squared like this. Now it'll be much easier to take the second derivative. So I get 0, bring down the 2, negative 2 cosecant x times the derivative of what's inside, which would be a negative cosecant x cotangent x. So the second derivative needs to be rewritten as 2. I have cosecant squared x and cotangent x. Well, I'm going to have a hard time setting that equal to 0, so I'm going to actually change it all into sines and cosines. So I have 2 times 1 over sine squared x times cosine x over sine x. So that would really give me 2 cosine x over sine cubed x. The bottom is not going to give me 0 in this interval because we're talking about an open interval. The top, I'm really asking myself, where is the cosine x equal to 0? And that would be at pi over 2. So it's going to change concavity at pi over 2. When I test this into my second derivative, when I plug in, say, pi over 4, I know that both of these are positive in pi over 4. So I know it's positive over here, where only the sine is positive when I plug in 3 pi over 4 into my second derivative, so this one has to be negative. This is just a sketch. It doesn't ask me to find intercepts or any of those other things, so I will not find those. There are no vertical asymptotes, there's no horizontal asymptotes, and none of those things. And I'm only talking about from 0 to pi, so that's the only part of the graph I'm going to make. So we're going to just have pi over 4 and pi over 2 and 3 pi over 4 on the graph, as well as pi. And this is definitely not what your graphing calculator will show you, because I did not actually find those exact points, because all it did was ask me to sketch this, didn't ask me to use the exact sketch. So I'm going to decrease all the way to pi over 4. So I know there's a minimum right here, and then it's going to increase again all the way to 3 pi over 4. And this is all concave up, and then it changes over to be concave down, and it starts to decrease at that point. Again, this is not exactly what your graphing calculator will show you. You can punch it in your graphing calculator, you'll get something similar to this, where the concavity and the increasing and decreasing are the same, but it will not be the exact graph because we never found exact points on the graph.